Hello all, welcome to week 7, and this week we're going to be talking about there are two positions here. It is to do with identity over time, and the first one is called Perdurantism, and the other one's called Endurantism. And as we'll see, Perdurantism is the idea that things exist over time by having temporal parts, whereas Endurantism is the view that things exist over time in virtue of being wholly and completely present at each time at which they exist. So those are going to be the views that we're going to look at coming up, and it's to do with how a thing at one time can be identical with a thing at another time. So identity is our topic, but it's identity over time specifically. But before we get to identity over time, I want to talk a bit about identity itself. So I want to give some background to fill in a few details, things that are kind of going on in the background of the chapter in the textbook. I want to fill in those details a little bit and try and talk a bit about identity in general. So for this video we're not really going to be talking about Perdurantism and Endurantism at all. We're going to be giving this background stuff or background detail on the notion of identity. So, the first thing to say here about identity is that it's often said to be a relation, and that's a kind of a formal definition. So, if we remember, we talked a bit about the before than and after than relation, which is a relation that holds between different events. And that was a relation because it's got two empty gaps in it. If you remember, that was the way of putting it. If you say something is before something, it's got two gaps that need to be filled. And identity is the same in that sense. So formally, it's a relation because it's got two empty gaps in it. I'll spell out what this means in a bit more detail. But I'd want to caution you, and really, it's a bit misleading to call it a relation as well. So I'm going to try to bring out these issues first of all. So, let's just talk about some other... Well, the other thing is the before than and after than relation that I've just mentioned is a relation that holds between events. Identity is first and foremost, a relation that holds between objects, I would say. Although it could hold between events as well. It's a very general relation, if it's to be thought of a relation at all. So here, there's the symbol for identity, and we say things like, let's just use Superman and Clark Kent. Superman is identical with Clark Kent. Now, I assume everybody knows, by the way, the Superman. It's a classic example that's often used because everybody knows the story, or seen a film or whatever. I presume that everybody knows that in the Superman stories, Clark Kent is Superman. He's one and the same thing as Superman. When he's working in his normal everyday life, wearing a suit and tie, nobody knows that he's Superman. He calls himself Clark Kent. But then when he reveals him, he puts on his cape and he flies around, he's Superman. So this here expresses just the fact that Superman and Clark Kent are one and the same thing, right? And that's what identity means. It's related to being one and the same thing. So this is to be understood then in terms of numerical identity, and that's our topic really, numerical identity. When we say one thing is identical with another, here we can just put that in general. If we say that one thing is identical with another, that A is identical with B, really, that form of words isn't quite right. One thing is identical with another thing. Well, what it actually means is that the other thing isn't really another thing at all. It's just the same thing as the first thing we mentioned. So you can't really say one thing is identical with another, because one thing is never in fact identical with another thing. If it's another thing, it's not identical because it's a different thing. I hope that makes sense. It's just a problem of expressing it using natural language. So really, one way of thinking about this, if we have this idea that A is identical with B, what we really mean is that A and B, we can understand this as saying something like A names the very same thing as B, right? And that's why I say it's perhaps not properly thought of as a relation, because a relation is normally thought to be it holds between one thing and another thing. So let's give some examples of relations. So being taller than, so we'd have is taller than. If you have A is taller than B, so here notice the is taller than has got two gaps, needs to be filled. That's why it's a relation. Well, here, well, we can have two things in there, so we can have I don't know, something like I don't know, Trump is taller than Obama, something like that. So yeah, there we've got Trump one thing, Obama another thing, and they stand in this relation of one being taller than the other. Okay, but notice that when we're talking about identity here, it can never be that we get a true sentence if we put two names. So we can't have Trump is identical with Obama. Obviously that's false. In fact, yeah, we can, if we ever put a name for one thing and a name for another thing on either side of the identity relation sign, we're never going to get a true sentence. So, okay, this is just to say it's thought of as being a relation because formally if you put equals it's got two gaps, right? So it needs to be filled in with two names. But, I mean, if we get a true sentence here, basically we've filled either side with two different names for the same thing. So to say that one thing is identical with another is a bit misleading because one thing can never be identical with another. Really what you're saying is that this thing known under one name is identical with another thing. Well, you see, you can't say it in English. This thing known under one name is identical with this thing known under this name. I.e., those two names pick out the same thing, they're one and the same. Okay? So it's to do with numerical identity. By the way, the reason then I've talked about numerical identity here is that, well, we sometimes, there's another notion, let's clear this off. So we're interested in numerical identity, which is the idea of being one and the same thing, and the same thing. But there's also the idea of qualitative identity. Qualitative identity. So qualitative here, quality is like another word for property. So you can think about this as being identical with respect to properties. So sharing the same properties. Sharing the same properties. And sometimes we say that things are identical when we mean that they share all the same properties. So take an example. Suppose we've got, I don't know, a vase. I don't know why I picked a vase, by the way, but anyway, there's a vase. And then suppose that we've got another vase over here. Okay. And we can imagine that they are, I mean, I haven't drawn them very well there, but we can imagine that they are the same colour. Two red vases. They're the same shape, they're the same size. Molecule for molecule, if you zoom in on them, you can't tell any difference between them in terms of their properties. So there's an idea here that they share all of their intrinsic properties at least. And then you might say, look, this vase is identical with this vase. Okay, this vase here is identical with this vase here. But obviously, you don't mean that they are one and the same thing. When we say that things are identical in that sense, we're not expressing we're not using numerical identity. When we say that this vase is identical with this vase, we're expressing qualitative identity. We mean that they've got the same qualities, so we've got the same properties, right? And that's not the sense of identity that we're going to be interested in. You know, I mean, this is used in things like identical twins. When people say that, oh, they're identical twins, obviously you don't mean that there's only one thing there, there's one person. There are two people, and they just happen to share many of their properties. I mean, no two twins are ever completely qualitatively identical. There's always going to be some differences. One might have a mole in one place where one doesn't. But, you know, it's an approximation. When we say that they're identical, we mean they are very much alike with regards to their properties. Okay? But anyway, that's the sense of qualitative identity, not numerical identity. Okay? So, just to emphasize again, when we use that symbol, the identity symbol, it's to be understood as expressing numerical identity, being one and the same thing as, and not qualitative identity. But I do want to say a little bit more about the idea of properties here, because there are people who see a link between numerical identity and qualitative identity, or at least with the idea of properties, so I'll try and bring that out now. So the link that some people see can be expressed in two principles, these are thought to be metaphysical principles, one of which is accepted as being true by nearly everybody. The other one is, well, it's contentious, but most people reject it. I'm not sure that we should, but okay. This is, first of all, let's put the identity of indiscernibles, and we'll see these have got rather similar names. So the first principle is the identity of indiscernibles. Indiscernibles. And the second one is called the indiscernibility of identicals. Indiscernibility of identicals. I'll give that a capital. It's the name of a principle. So the identity of indiscernibles says if a thing X and a thing Y, and when we use this way of putting things in terms of X and Y, this is to avoid the problem of natural language, which I just pointed out here. And that problem was that when we say, you know, this thing and another thing, it already expresses the idea that the other thing is not the same thing as the first one. The phrase another thing means non-identical thing. And we here avoid that, because when we say a thing X and a thing Y, well, we're using just two variables, X and Y, but we're not saying that whether they're the same thing or different things. So here X and Y might be variables for the same thing, there might be variables for different things. So at the moment, you know, a thing X and a thing Y, we're not saying anything about their identity with that. Maybe X is the same thing as Y, maybe it isn't. So that's why we use this. So a thing X and a thing Y, if a thing X and a thing Y share all of their properties, then they are identical. Numerically identical. Maybe I'll put that in. So there's the first principle, and I'll speak a bit more about them in a minute. I'll lay the two principles out and have a think about which one of these you think is the one that's obviously true, and which one of these is the thing that you think is perhaps false. Anyway, indiscernibility of identicals says if a thing X, so it goes in the other direction, is identical with a thing Y, then X and Y share all of their properties. Okay. So, okay. Have a little think about, so the first one, if a thing X and a thing Y share all of their properties, then they are numerically identical. Then they are, in effect, X and Y are the same thing. Whereas indiscernibility of identical says if a thing X is identical with a thing Y, so if they are one and the same thing, then X and Y share all of their properties. So, have a reflect upon it, pause the video if you want, but if not, here's the answer. Well, This one is the one that's generally accepted as being obviously true. This one is the one which is disputed. And it should be fairly clear why, because look, I mean, if a thing X is identical with the thing Y, then X and Y share all of their properties. Well, they have to, surely. I mean, it's just, isn't it obviously true? Because it's just saying, if you've got, Superman and Clark Kent, well, they're the same thing. So they share all of their properties. One can fly, the other can fly. Well, why? Because there's not one and the other. They are one. They are the same thing. So of course they must share their properties. In fact, it's not really their properties. It's basically saying everything shares the property. Everything has the same properties as itself. I mean, it's almost trivial once you understand it in that way, and that's why it's usually thought, or pretty much universally agreed, that the indiscernibility of identicals is true. Okay. Whereas the identity of indiscernibles, well, if a thing X and a thing Y share all of their properties, then they're numerically identical. You might already think, well, we've just seen an example of when that's false, because we've just seen these two vases which can be absolutely, they can share all of their properties. They're the same colour, the same shape, the same size, but they're not numerically identical. So surely the indiscernibility of the identity of indiscernibles is false, you might say. But things are not quite so simple as that, and I'm gonna raise a classic problem here, because look, when we talk about the two vases, I've already sort of mentioned this. They are intrinsically the same. They've got the same intrinsic properties, but they're relationally different. So, if you've got two vases, so suppose we've got some sort of a shelf here, and we've got one vase over here on the edge of the shelf here, and then we've got, we've got a couple of books in the middle, and then let's have a candle, something like that. And then here's the other vase on the other side of the shelf. Well, yes, they do share all of their intrinsic properties. They are the same in every respect if we just look at the kind of, the intrinsic properties of these things. Look at the properties they have in and of themselves. But they do differ in their relational properties. So this vase here has got the property of being next to some books, whereas this vase here has got the property of being next to a candle. So they differ in those respects, and in that sense then they don't share all of their properties, right? They share all of their intrinsic properties, but not all of their properties. Okay, so we've got this question about, alright then, suppose we understand the indiscernibility of identicals here as literally meaning all of the properties. That is, not only their intrinsic but also their relational properties. Maybe then it's true. If there's one thing and another thing, and they not only share all of their intrinsic properties, but they're all you can't tell them apart by looking at their. If you can't tell them apart by the relational properties either, then maybe they are one and the same thing. Okay, I'm going to say a little bit more about that in a minute, but I just want to, before I do that, so basically we're going to ignore this second one for the moment, the indiscernibility of identicals. In fact, we're going to ignore it completely, really. That one's just true, so don't take this drawing here. This drawing's associated with that, the example I gave of that. The indiscernibility, just true. If one thing is the same as another thing, then actually they're not the same thing. They're the same. They're not different things after all. They're the same thing, and therefore they must share all of their properties, because everything shares the same properties with itself. Fairly obvious, it looks like. We will come back to this a little bit in the second video. But okay, then we've got this other principle that we are going to have a look at in a bit more detail in a minute. Before I do that, though, I just want to give you the formal mode of these, just so you can see it. Don't worry if you don't follow this, but for those who are interested, this one here says if a thing X and a thing Y share all of their properties, so we have for all X and for all Y, if fx, if and only if fy, so here for everything X and everything Y, if X is F, if and only if Y is F, so, right, where these stand for, we might need to quantify other properties at the beginning of this, but often we don't, so anyway, then, so if that's true, then x is identical with y. Okay. So there's that principle. So notice you've got this idea, if two things, or if a thing x and a thing y are the same with respect to all their properties, then they're identical. And down here, we just go in the other direction. So for all x and all y, if x is identical with y, then fx, if and only if, fy for all properties f. Okay, so if x and y are the same thing, then they share all of their properties. So, okay, you can see then really the difference between these two principles is the direction of this implication, this arrow. So there it is in the formal mode, in case that is of any interest to people. Yeah. By the way, there's also, just so you also know, there's a thing often called Leibniz's law. Well, it's actually unclear what Leibniz's law is. Some people use Leibniz's law for this principle, and some people use it for a combination of the two principles together. So they use it for kind of this principle and this principle joined together. And we get the principle joined together just by putting in, so we can have for all x and all y, x is identical with y, if and only if fx, if and only if fy. Don't worry too much about this, but okay, be aware Leibniz's law is sometimes used in relation to these two principles because Gottfried Wilhelm Leibniz, what was he, 17th century philosopher? Sorry, 18th century philosopher, who we've already seen in he had disputes with Newton, but he basically talked a lot about these two principles, the identity of indiscernibles, and endorsed them. Alright, so now I want to, well, I'll tell you what, let's just clear that off, and I'll put up the identity of indiscernibles again. So now I want to think a bit more about this principle, the identity of indiscernibles. And again, let's state it. If a thing x and a thing y, thing y have all the same properties. I stated it before by saying share all of their properties. Again, perhaps not the best way of putting it, given there is plural and there therefore presupposes there's two. So we'll put it like this. If a thing x and a thing y have all the same properties, then x is identical with y. Okay. Why might somebody believe that this is in fact true? And I'll give a kind of an argument for this. It's often associated, so there's another debate in metaphysics about what objects are and what their relation is to properties. I think I mentioned this in the very first video of this module. And the debate is, basically we can think about it like this. Let's take, let's not have a vase, let's have a good old table. There we are, good old table. And let's have it being I forgot a brown pen. What's this? A rainbow pen? Oh, no, I don't want that. Okay, green. It's a green table. Okay. Green table. The thought here goes something like this. You say, well, okay, here's an object, a table, and it's got certain properties. It's got a certain, so first of all, it's green. It's got a colour. It's green. Let's suppose it weighs, I don't know, what would a table weigh? 50 kilos in weight, or in mass. It's a certain shape, it's table shaped. So if we list all of its properties like this, bum 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 bum, every single property that it's got, intrinsic property, let's say, for now. And the thought is, well, once we've listed all of the tables, I mean, here we're thinking about an object as being a thing, and the properties as being kind of stuck in it like pins in a pincushion. This is a kind of standard model. But the thought here is, well, once we've listed all the properties, what's left of the thing itself? I mean, everything that you can see about this table here is a property. You know, you can see. So, I mean, do we really have to think that there is this thing that possesses these properties, an independently existing thing? The view that there is some kind of a kind of thing that possesses the properties, so independent of the properties, you've got this kind of metaphysical object, is associated with John Locke. So John Locke held the view that there is, you know, this picture here where we've got an object and properties being separate, two different, so properties are a type of, I don't know, metaphysical entity, and objects are another type of metaphysical entity, and what we've got here is a kind of an object instantiating properties, right? Well, that those two things are really there. You know, you've got objects and the properties is associated with Locke, and he called the underlying object the substratum, the thing which underlies the properties and possesses the properties. Okay. So yes, this is a substratum view. But there are some people who have held, and this is most famously associated with David Hume, although David Hume himself didn't hold this, or didn't express this view with regards to all objects. He expressed it with regards to human or persons, so, you know, the mind in particular. So you might remember this, that David Hume had this bundle theory of the mind. He thought that there is no, as it were, substratum to the self. There is no thing which has all the mental properties that you take yourself to have. Rather, the self, he thought, was a bundle of perceptions, a bundle of experiences. So, nonetheless, the view generalizes, and this is called the bundle theory. So the bundle theory says, well, actually, there is nothing more to the object than its properties combined together. There is no substratum, no thing underlying the object. This picture that we've got, this kind of picture over here, is wrong, he thought. In fact, you know, well, I'll redraw it. It's like, why think that there's an object that somehow instantiates the properties? Well, you know, just get rid of the idea that there's an object altogether and take the object itself to be just the bundle of properties. So what is the table? Well, it's just the kind of bundle of the properties, being green, being 50 kilos in mass, being table-shaped. You know, that's all that you ever see. You just see these bundles of properties. Well, that's what objects are. It's weird to think that there is this somehow, as Locke even admitted that this substratum is a I know not what. It's something that, because as soon as you mention something about a substratum, well, you're talking about a property, and right? So the Humean view, or the bundle theory view, inspired by Hume, I think it's probably better to say than held by Hume, because, as mentioned, Hume only really talked about it with regards to the mind. So this bundle theory view basically says, well, look, it's weird to think that there is this kind of underlying thing that you can never actually get a handle on. No point in admitting it. Occam's razor, that you always ought to accept the simplest hypothesis. Don't multiply entities beyond necessity. Kind of tells you that, you know, this is an idle posit, this substratum. You don't need it. You can think of objects as just being bundles of properties. So that's how we should think about them, and that's how we should believe they are. Okay, now, if we take this view then, suppose we take the bundle theory, then, I don't want to clear the canvas, I want to leave the identity of indiscernibles. Oops, up. Oh. If we take the bundle theory, and we think about objects as being just made up of their properties, and there's nothing else, if we include relational properties in there now, so we think, well, an object is not just a bundle of its intrinsic properties, it's a bundle of all of its properties. Well, then it looks like we've got a reason to believe the identity of indiscernibles, because if a thing X and a thing Y have all of the same properties, so I mean, let's take a, oops, this is just representing a bundle, and suppose it's got a property F1, F2, F. So we're now imagining that we can number all of the properties that there are. So F1 might be being green, F2 might be, in fact, let's give them different numbers. It's got property F1, property F20, property F3474. Let's just leave it at that. It's just got these three properties. So these just label properties that things have got, right? And really, this object just is the bundle of these properties. So perhaps this circle around it doesn't make sense. It's a kind, or that's just to express that these properties are bundled together. And the thought is, well, okay, here's another object over here, and suppose, I mean, I shouldn't really say another object. Here's an object over here, and it's got. Okay, I have to explain this a bit more. These are not really. We're not really thinking about these things as being in space. We're just, okay, this is kind of like, okay, I'm drawing a little representation of an object, and I'm drawing another little representation of an object over here, and it's got F3474. Here the thought is, well, look, here's one thing X, and here's one thing Y, which I've just represented schematically on the page. Are they the same thing, or are they different things? Well, if you hold the bundle theory, well, look, I mean, objects just are a bundle of their properties. Well, here's a bundle of these properties, and here's a bundle of the same properties, so surely they've got to be the same thing, because there's nothing more to an object. It's not like we can say, and there is some sort of a substratum associated with this one, and some substratum associated with this one, right, that makes them different. No, objects just are the bundles of their properties, so they've got to be the same thing, and that gives us a reason to believe the identity of indiscernibles. Let me see the idea. Anyway, most people still reject it, because if we now, in fact, let's do this, let's rub this bit out again. If we now do so this is a very famous paper from the 1950s called The Identity of Indiscernibles, and it was by a guy called Max Black. Oops. So Max Black. And he imagined a particular situation. He said, well, imagine that you've got a universe that contains nothing except two great big black spheres. So these now are meant to be spatially, right? So this is a black sphere. This is a black sphere. And he says, by the way, again, I haven't drawn these very well. I know I can see that they're different sizes, but we're to imagine that they are the same size, the same shape, they're made of the same stuff, and in fact, you can't tell them apart intrinsically. If they're the only two things that exist in the universe, and they don't share any intrinsic differences, it looks as though you want to say, well, okay, they're two things. But notice that they also share all of their relational properties. I mean, this one you might say, so suppose the gap separating them, if it makes sense in an otherwise empty universe, is 500 miles or something. So you've got to remember there's nothing else in this universe. You say, well, this black sphere here is 500 miles from another black sphere. Well, this black sphere also has the property of being 500 miles from... In other words, there's nothing you can say about the one sphere that you can't say about the other sphere. So it looks as though they share not only all of their intrinsic properties, but all of their relational properties as well. I mean, here you might say, well, look, one's on the left and one's on the right. But, yeah, there's no left and right. That presumes you've got an observer looking at them. I mean, I've had to draw it on the page, so I've had to presuppose an observer here. But in this universe, of course, these are the only things that exist, so you don't have a left and a right. There's no direction to the universe. So, at any rate, most people think that such a universe is possible, metaphysically possible. You could have a universe containing two identical things, two non-identical things, two spheres. And if there is, then you have to reject the bundle theory of properties, right? The bundle theory of objects, that according to which, because here the bundle theory would have to say, well, it's the same sphere located twice over. The debate does go on, by the way. Bundle theorists do defend themselves from this argument, but it's a strong argument to try to say, look, we can't think of objects as just being a bundle of their properties. There must be something else, some individuating thing about objects that makes them what they are. Why? Well, because here's a perfectly possible situation where things share all of their properties, intrinsic and relational, and yet there's two. So there must be something that makes one distinct from the other. Okay, and therefore people generally tend to reject this. I put the question mark before because it is disputed, but because of this kind of Max Black argument, people do reject this idea. If a thing X and a thing Y have all the same properties, then X is identical Y. Rejected. Okay. Hopefully that makes sense. So before I finish, the last thing that I want to do then, before I finish this video, the last thing that I want to do is to talk briefly then about properties of the identity relation. Okay, so I've already said it's not quite clear that we ought to understand it as being a relation as such, but nonetheless, when we write it down, it's got these two empty gaps in it, right? So it's thought of as being a relation in that sense. And okay, so the thing I want to mention here is this, and this is going to be important. So we do need to sort of bear this in mind as we go. In fact, all of what I said is kind of going to be important. It's not mentioned in the textbook, but this is background that I'm giving you so that you can really get to grips with the Endurantist and Perdurantist positions. And I'll say this, if you maybe I'll put this as a kind of a warning. I don't know what the right word is here, but I'll put it as a kind of a thing at the beginning of the video saying, look, I'm not expecting you to follow absolutely everything I'm not expecting you to finish this video and be absolutely clear about all the things that I'm talking about. I mean, philosophy doesn't work like that, right? As long as you're kind of following what I'm talking about and getting some bits and not others, that's okay. Philosophy is not, I mean, when we do it properly, it's not the kind of thing that you can be absolutely clear about. A lot of the things I'm talking about, I still have questions and sort of not sure I understand certain bits of it, and it's sort of working through to a greater understanding slowly. It's slow illumination. It's not. Sometimes you get a click, which makes some bit of it come into focus. But we're here talking through difficult conceptual issues. So, I think people often they'll kind of give up a bit too easily. They'll say, "Oh, I don't understand that bit," and they'll kind of switch off from the. I'd kind of urge you not to do that and to sort of just push on through and just think and try to get these issues clear. But don't worry if you've got unclarities. It's natural and normal. So okay, now then, the last thing that I say I want to talk about here is let's illustrate it first with some other types of relation. So imagine we take the taller than relation. So, and now we say, well, suppose that A is taller than B. And that B is taller than C. Right? What follows from that? Imagine we've got these as premises in an argument. A is taller than B, and B is taller than C. Well, we'd be able to conclude from that that A is taller than C. Hope you can see that. So, if we've got, let's draw some people. Here's A. A is taller than B, and B is taller than C, right? And it's fairly clear that if A is taller than B and B is taller than C, then it follows that, so take these arrows to be the taller than relation, then A is taller than C. Okay? And a relation that's like this is called a transitive relation. So a transitive relation is one such that if one thing bears that relation to another, and that second thing bears it to a third thing, then it follows that the first thing bears it to the third thing. That's a transitive relation. So other relations that are transitive are For example, being older than. If x is older than y and y is older than z, then x is older than z. That's true. What about how about being a brother of? If x is the brother of y and y is the brother of z, I think it follows that x is the brother of z. I think that's right. But other relations aren't transitive. So take the, I don't know, being a mother of relation. Yeah. So if x is a mother of y, and well, let's now, if we put that in, if we say if a, well, tell you what, let's just to make this clear. If a is the mother of b, and b is the mother, is the mother of c, it doesn't follow, you cannot conclude that a is the mother of c. In fact, right, does not follow. There the conclusion is an invalid inference. So that would be an invalid argument. Because if you've got one person, A, who is the mother of B, and B is the mother of C, then it's not the case that A is the mother of C. I don't know, barring some, I don't think you can get some weird kind of, I know some people have, when you give these relations, in terms of family relations, they bring in weird kind of time travel stories where people end up being the mother of themselves and things like that. At any rate, we're ignoring any kind of weird complications. Maybe there's some way to get the story to work, but I think you understand the idea. We're not bothered about this particular example. It's the principle that matters, that a transitive relation is one that has these features. So the reason why I want to bring this or mention this is for the following reason. Well, identity is transitive. So if we have A is identical with B, and then we have B is identical with C, it follows that A is identical with C. Right? That's should be fairly clear. Basically if A and B are one and the same thing, and B and C are one and the same thing, well then A and C are one and the same thing. That's all it says. So okay, this is the idea that identity is transitive. Okay, I'll write that again. Transitive. Identity is transitive. That's a T. Okay, so there's the first property of the identity relation. It's a transitive relation. So, second up, now suppose that we've got A is identical with B. Sorry, let's illustrate again with another. I'm not going to go into such detail, but we'll go A is the same height as B. We can conclude from that that B is the same height. That's as A. It's fairly obvious. If A is the same height as B, then B is the same height as A. That's a valid inference. And a relation that has this property, that you can, from the fact that the relation holds in one direction, you can infer that it holds in the other direction, as it were. This is called a symmetrical relation. So this is symmetrical. Take the taller than relation again, and you'll see that that's an example of a property, or a relation, that is not symmetrical. So if A is taller than B, it doesn't follow that B is taller than A. In fact, it can't. It never follows. So the taller than relation is an anti-symmetrical relation, whereas, for example, the same height as relation is a symmetrical relation. Right? So others are like being the same age as, being in the same room as, and so on. If A is in the same room as B, then B is in the same room as A. These are all symmetrical relations. Okay, so the reason why I'm mentioning this is because identity is symmetrical. If A is identical to B, this might all seem very obvious, but you'll see there's a reason why we mention it. Then B is identical with A. Okay, so identity is symmetrical. Finally then, consider a relation. Again, we can use the being the same height as relation. Being the same height as, oh well, let's put it as is the same height as. And notice that we can plug the same name in on both sides of this. So for everything that has a height, it's always going to be that that thing is the same height as itself. So we can say for all things that have got a height, for all things x is the same height as x is a true sentence, is a true statement, right? So that's just to say any property that any relation that has this kind of a feature to it, that everything bears it to itself, is said to be a reflexive relation. Okay, so reflexive relation is one that such that everything that has or bears this relation to anything at all bears it to itself, right? So we should put that for all things x that stand in the same height as relation to anything else, they stand in that relation to themselves in every case. So a reflexive relation. Okay. So again, notice that the taller than relation is not reflexive. So nobody is taller than themselves. That relation doesn't bear between a thing and itself. Whereas things like same height, same age, those are all reflexive. And the reason I'm mentioning this is because, well, for all things x, x is identical with x is true. So identity is a reflexive relation. Okay, everything bears it to itself. And in fact then we can say the following: identity is one, well, reflexive, let's put them in this way. Number two, symmetrical. And number three, transitive. So identity is reflexive, symmetrical and transitive. And that's going to turn out to be important in what follows. Okay, well I've been speaking now for this has been quite a long sort of introductory video, but all of this stuff now we're going to see how it bears on identity over time. So we've been specifically thinking here about just identity in general, some of the general features of identity. We're now going to move on to identity over time. Okay, thanks.